the all-stars. Okay, real-life applications. So that's just fancy words for word problems.
Don't you do a lot of real-life applications in physics? It's like Alg2 and calculus of just real-life applications.
Yep. So word problems are always a good news, bad news situation. And it's not, there's one set of stuff that's good news and one set that's bad news. It depends on the person as to whether it's good news or bad news. Because with word problems, you have to read carefully. So that's good news for some people, but it's bad news for others. But you've got to read carefully. And then, again, this is great news for some and terrible news for others. You have to think. I know. It's good news for some, bad news for others. Categorize yourself accordingly. Because we're not going to, there's no new formulas. Right? This uses math that you're supposed to already know anyway. So, again, this may be good news or bad news. I hope that's good news. There's nothing more to learn. You already know it. But some people, they don't want to think, they just want to plug in numbers. That doesn't work for word problems. You have to think about what's written, interpret what's written, use the formulas you know. Also means there's no memorization. So again, depending on who you are, maybe this is good news, maybe this is bad news. I mean, I hope it's good news. There's nothing more to learn. We're just going to read carefully and use what we already know.
When's the test?
Not for a while. March 4th, 5th.
Block days? It's a 2-day test again?
Oh, it's a block day. So our test would be the 4th. Yeah. Okay. Draw a picture. It says must, and then for draw a picture, I'm going to say maybe, because not all of these really require a picture. But we do need to define the variable, meaning, gentlemen and ladies, define the variable means it's not going to tell you what variable to use. You have to figure out, what variable should I use? You get to pick, but you got to pick and say what variable you're using. We'll write the equation, solve the problem, algebraically or graphically. So we do get to use our calculator on this section. Draw the graph, label the critical points, find all solutions. If only one solution is used for your answer, explain why the others are not valid. Okay, so let me try to explain what that means or when we would use that. A lot of times we're going to end up looking for zeros. So we'll graph something. We're looking for zeros. Trying to pause to give you a minute to sketch that graph. How many zeros does that graph have? 1, 2, 3. And then depending on the problem, maybe some of those are good and maybe they're not good. Liam, I think you just heard, what did you say a minute ago?
Have negative distance.
Right, so if we're trying to find, how long a piece of lumber is or how tall the flagpole is, and we end up with negatives, well, you can't have negative distances, so maybe you throw out the negatives. I have to say maybe, because maybe the problem is set up where negative numbers are okay. Again, read carefully and think, and maybe you keep the negatives, maybe you don't. It just depends on the problem. But that's what that sentence is referring to. All right, number 1. Again, there's no magic formulas, there's no magic method. You just have to read carefully and figure out what formula you need to solve that particular problem. A storage company needs to design a new storage box that has twice the volume of its largest box. Its largest box is 5 feet long, 4 feet wide, 3 feet high. The new box must be formed by increasing each dimension by the same amount. Find the increase in each dimension. Okay, maybe we should just start with that. When we say increasing each dimension by the same amount, what does that mean?
So plus 2 on each one.
Okay, we'll add the same amount to each one. Will we increase? We'll add 2 to each one, or 7, or 12. Like, who knows? We got a box, and we're going to increase each dimension by whatever the same amount is. Okay. The volume. Its largest box is. What's the formula for the volume of a box?
Like times this times twice.
So the old box is just 5 times 4 times 3. That doesn't help me directly, but I am going to need that number. 5 times 4 is 20. 20 times 3 is 60. So the old box is 60. What's that mean the new box is going to be? 120. Because the new box is twice as big. So something's got to multiply to 120 because the new box is twice as big as the old box. Okay, and we're going to increase each dimension by the same amount. So if the old length was 5, by the same amount. That's what we're trying to find. So let's call x the amount of increase. This is us defining our variable. We're going to use x. X is going to represent how much we add on to each side. Now I can answer. The old length was 5. What will I use for the new length? 5 plus x. I'm going to add x on to 5. Now the rest follow the same pattern. So what's the new width going to be?
4 plus x.
And the new height?
3 plus x.
3 plus x. So I took my 5, my 4, and my 3. I added x to each of them. Now my new volume is 120. It offered me the calculator to do this. So let's see. Meaning I don't really have to multiply this out. If I did, what would the degree be? If I multiply this all out,
X to the third.
it'd be x to the third. Which means I definitely don't want to be solving that by hand. Right? If it was x squared, I could do it by hand pretty easily. But x cubed, I don't want to mess with that. So I'm going to do this in the calculator. And in the calculator, I like to find zeros. But if I want to find zeros, that means I need to make this thing equal to 0.
You just plug in that equation like that in the calculator. But you have to move to the 120 over.
I want to move the 120 over. Do you know why I want to move the 120 over?
You can have a y that it would have to equal 0.
I want it to equal 0. There's a way to do it with the 120, but then you have to graph 120 and all of this and find where they intersect. It's more of a pain. Let's just move the 120 over. The calculator is set up to find zeros. It's not set up to find 120s. Let's move the 120 over. And then we can put all of that in for y1. Conceptually, it's probably easier to figure out where this is equal to 120, but in the calculator, it's much easier to find zeros. So let's move the 120 over, put that in for y1. Your graph may need to be zoom standard because we're doing some weird graphs later on. Okay, 5 plus x, 4 plus x, 3 plus x, minus 120. Careful with the parentheses. Okay, I'll look at the graph. How many zeros does this one have? 1. What's the easiest way to find zeros? Doesn't always work, but yeah, let's look at the table, see if that helps. So, second table. What do we think? Good news or not?
Yes.
What am I looking at? What's the good news part?
Y equals 0.
Y equals 0, x is 1. x equals 1 is a solution to that equation. So that means we'll add 1. If we add 1 to each dimension, we get 120. You know what? Let's check that, just because this is an easy check. 5 plus 1, 4 plus 1, 3 plus 1. That's my new box. 6 by 5 by 4. Let's see. 30 times 4 is 120. So yes, if we add 1 to each length, we end up doubling the volume of the box. And again, there's no magic in that. The only formula was length times width times height, but you had to read carefully. Questions on number 1? All right, number 2. An open box is to be made, looking for my open box, from a square piece of material with side length of 10 inches by cutting equal squares from the corners and turning up the sides.
What does that mean?
Yes, what does that mean? Okay, we start with a square piece of material.
How big?
10 by 10.
It's definitely not drawn to scale. For me.
I was going to say, mine looks pretty close to a square. I'm going to cut a corner, like a square corner from each corner. I'm going to cut out a square from each corner, an equal size square. And then if I folded it on these lines, on these dotted lines, I think I would have a box. Some people can visualize that easily. Other people need to see a rectangle. So this is a little bit different. It's not a square, but same idea where I cut a square from each corner. And if they were equal squares, or if there were squares at all, that one's not, but if there were squares, when I folded it up, then I'd have an open top box. So this one's a rectangle, this one's a square, but same idea. Cut a square from each corner, fold it up, and now I've got a box. We okay with that now?
Yes.
That's a weird explanation maybe, but very common calculus problem especially. But now we're doing algebra. Okay, what size of square? So we want to know, like, well, what size are these cutouts over here? That's our variable. Maybe overkill to label all of them.
Wait, what letters?
I use an X. So X is the side length of the cutout square. I suppose you could have used L. I don't know what other variable would have. S for square. What size of square would you cut out if the volume of the box, another volume of box, is 48? Okay, so 48 has to equal length times width times height. I wrote those kind of spread out because we're going to put stuff in them. I think the height is actually the easiest one. So if my small square is X by X, when I fold it up, right, how tall is my box? X. So that length became, or that square length there, became the height of the box. So my height is X. So now I need the length and the width. Well, it was 10 all the way across. But how much? I cut some of it off.
10 minus X.
10 minus
2X.
I cut off X from this side
2 corners.
and X from this side.
2 minus 2.
Oh, wait. X. Wait.
Somebody said it over there.
10 minus X squared?
not x squared. I cut off this x and I cut off this x. So now that width is 10 minus 2x. Started with 10. And it's the same way for this way. I cut off x from both sides. This is a bad example because this wasn't a square to start with. But I cut off x from both ends. So 10 minus 2x, 10 minus 2x, and x. So yes, I plug it in, but before I plug it in though, what am I going to do? Move the 48 over, so I have a 0. It's much easier to look for zeros than it is to look for 48s. Is there a more convenient way to write, or efficient way to write 10 minus 2x times 10 minus 2x? Don't have to do it, but it might save a little space. And certainly when you're typing things in the calculator, maybe it makes it a little easier to type that in. So 10 minus 2x squared times x minus 48. And if I write it like that, I can get the whole thing on the line there. Alright. I know the table is the easier way to go, but the graph is the quicker way to visualize how many answers do we have. 3. So 3 zeros. Are any of my zeros negative? No. So I think I'll be okay with these 3. Let's go to the table. Maybe we get a cheap one here, an easy one. Yes, we get 3. You could list it first because we found it first, but I can tell by looking at the graph that 3 is the middle one, so I'm going to list it in the middle. It doesn't matter what order you put them in. Okay, so I got that one from the table. How am I going to find the others? Yep. Calc 0. Second calc 0. Okay, be careful. I think we've run into this before, and there's 2 ways around it. If I'm trying to find my left bound, it's like that's okay for a right bound. If I go to the left bound, it's off the page or off the graph.
That's good.
That's fine as long as you know where it is. Like I'm going to push the left button, so I'm one left. I can tell by my y equals that I'm below it, so I'm going to use that as my left bound, even though I can't see the cursor. Now it asks for the right bound. I can see the right bound, so that one's a little nicer. And then press enter for guess. 0.628. Need to go do the same thing for that last one. Second calc 0. Where is it? Oh, there it went. Oh, I've got the same issue. I can find my right bound on the graph, but I can't find the left bound. If that bothers you, you can go to Window and change your Y values to see more. To visualize more of the graph. You don't have to do that if you trust where your cursor is. Second calc 0. But it is a little more convenient if you can actually see the cursor when you're at your left bound. There it is. Left bound, right bound. Guess. 6.372. I think it always says round to the thousandth, so we're going to go round to the thousandths. tenths, hundredths, thousandths. Okay, all those are positive, so that's good. But look carefully at those answers, and look at your picture, and look at the answers, and look at the picture. And I'm going to suggest that one of those won't actually work. Why not?
Because if you cut that out from both sides, it'd be 12.
Right. If I cut 6 from both sides,
It'd be bigger than the whole thing.
that's bigger than the whole thing. I don't have any box left. So I end up with negative side links. There's no box left. I've got to throw that one out. However you want to justify that, I'm going to say no box left. Some of you said that 12 is bigger than 10. Like, however you want to phrase it to justify that won't work. There are 2 that work. I think that's okay. One's a shallow box. Maybe this is the 0.628. 3 inches would be a taller box, but a smaller base. And I guess they counter each other, and they both end up at 48. So 2 answers that work, 1 that doesn't. Should we check the other 2? Oh, you probably should check the other 2. Don't have to.
What size of square do you need for like 9?
You're right. Let's make sure we answer the question. What size of the square? I'm going to say 3 by 3 or 0.628 by 0.628. But you're right, Liam. If it had asked for the area of the square, then it would be 9 and whatever 0.628 times 0.628 is. All right, the old open top box. All right, little side note. In calculus, you learn how to maximize the volume of that box. So like how big should the squares be so that the volume is maximum, right? Because if you cut small squares, then you got a big base but a small height. If you cut big squares, you got a big height but a small base. So somewhere in the middle is a maximum volume. But that's for calculus. Number 3. Several popular models of carry-on luggage have a length of 10 inches greater than their depth. The length is 10 greater than the depth. You know what? Let's turn that into math equation right now. Adam, can you turn that into a math equation? The length is 10 greater than the depth.
Would depth be like height?
Yep, you can use H for depth if you want.
So, length equals H plus 10.
Perfect. Okay, so we're using H for depth. We'll use L for length and W for width. Maybe we should use D for depth, but you get to pick. Adam thought H is height is a better word than depth, so we use H. That's fine. Okay, let's read some more. To comply with airline regulations, the sum, what's sum mean?
Total.
Yeah, what's the math word? Total is okay, but give me a better, more specific word. Not perimeter, not equal.
Multiple.
Addition. That's the word we're looking for. So the addition of the length, width, and height, depth, may not exceed 40 inches. So, Carter, can you turn that statement into a mathy statement? The sum of the length and width and depth may not exceed 40 inches.
L plus W plus D is less than 40.
I like it. I'm going to switch your D to an H because Adam picked H to start with. But if you're working the problem with D instead of H, that's fine. So what you said is right. May not exceed 40 inches. So I like it's got to be less than 40, but is it okay if it's equal to 40? Yeah.
Less.
So less than or equal to. Again, that's one of those, you just got to read the problem carefully. It doesn't say that, but we can equal 40 and not exceed 40. Write a function v of x to represent the volume of the luggage. Well, let's start with the easy part. Volume is length times width times height. Or L times W times D if you're using D. But I've got some information over here that I can use. Like I can replace L with H plus 10. So instead of L, I'm going to go H plus 10. And in fact, in place of L, I can go H plus 10. And peeking ahead, we want maximum volume, so I'm not worried about less than 40. I want this suitcase to be as big as possible, so I'm just going to say equal 40. All right, so what does W equal? Can you solve for W though? Tight on space here. It's a lot of work. So subtract everything to the other side. 30 minus 2h. So in place of W, I can put 30 minus 2h. And then I've got h. So now I've got a volume in terms of just h. Yeah, because I got the length is h plus 10. That was me not showing much work right here. If I subtract the 10 over, then I have W plus 2h equals 30. And then if I subtract the 2h over. Okay, so this time I don't know the volume, but I want to achieve a maximum volume. So I can put all of this in for y1, and what will I be looking for? That's the volume. I don't want the volume to be 40. I want the volume to be as much as possible. So I'm not looking for zeros. I want to know where that equation is the maximum. And that's one of our options under the second calc thing. So x plus 10, 30 minus 2 times x times x. Okay, that's my volume equation. If I go to zoom standard, not very helpful. Right, I see part of a graph way over here. Let's think about this. H, so my x is my height. I'm trying to think what scale I need to use. I don't need to see any negatives at all, but maybe I need to go a little further in the x direction. I'm trying to get a sense for my volume here. If each of the dimensions was 10, I mean that wouldn't even add up to 40, but what's 10 times 10 times 10? I'm trying to do easy math here. 10 times 10 times 10? 1,000. So that means my volume is probably 1,000 or more. So I'm going to change my y max to be 1,000. That still may not be enough, but 10 is definitely not getting the job done. So I'm going to go to 1,000 and see if that... Nope, that's still not enough. But at least I'm in the ballpark now. So any guesses as how high we should go on that? I don't even know. Back to window.
2,000.
We double it? Let's see.
Double it.
Let's get a guess. Let's see. Oh, almost. Although we can do the bounds without having to actually see the maximum. So you could do that and find the max even though it's not on the picture. But that bothers some people, me included maybe. So I'll go 2,500. I think we can see it if we go that high. There we go. So I'm looking for that maximum. Second calc, maximum, and remember it walks you through the same steps. Left bound means get left of the mountain. Right bound means get to the right of the mountain. Guess means you can just hit enter again. So let's be careful to answer the right question here. X is 8.931. But it didn't really ask me for X. It says, what are the dimensions of the luggage? So I got to go back and figure out the others. So height is 8.931. Got to start looking back through my problem here. How can I figure out what length is?
Not plus 10.
Not plus 10, because length is height plus 10. So I don't need a calculator to add 10. And then my width, got an equation for that. 30 minus 2h. So 30 minus 2 times 8.931. 12.138. Well, now it says, well, what is the maximum volume? So how can I get the maximum volume? If I know the length and width and height, multiply them together. Also, if I was really paying attention, it gave me the max volume over here. So the X value was 8.931, and then the height or the volume was 2052.205. A lot of work. The only math equation we used was length times width times height is volume. So you knew that one. Had to read, think, use the calculator, be careful. Alright, my suggestion for you, or today's assignment, is going to be 4 and 5. 4 is going to be a Calc 0 problem. 5, I can peek ahead and say largest area. So what do you think you'll be using on number 5? A maximum. So try 4 and 5. Again, that'll get us through half the worksheet, but tomorrow is also more practice on the worksheet. So you can take 2 days.